Thank you. Let me start by thanking the organizers, especially Subhro, for inviting me here. And it's a really nice experience with many interesting talk, many new ideas. And I'm going to talk about, as announced, engineering topological phases. I start with a disclaimer. There are actually two disclaimers. The first one is this talk will be from a materials perspective, unlike many of the talks in this conference, and will be of different flavor, I think, also compared to other talks, because I think other than Manish Jain, I'm the only representative from the first principles community. And the second disclaimer is yesterday night we celebrated the Christmas with all these friends and the partners in crime. I don't see them in the audience, so you can imagine how happy we were. We were very merry. And so if I sound, I see one of the partner in crime at least. So if I sound a little incoherent, you just blame it to yesterday's party. So we are living in this age of what I think is the recent excitement with the topology and etc. That's a topology Jew. We start with started with the excitement with the quantum Hall, then came graphene, the quantum spin Hall, a topological insulator, Marana, the previous talk was wild semi-metal, and it basically kind of ranges a broad spectrum. We have topological phases in the gapped matter, namely the insulator, to the gapless system, namely the metals. So the topology is kind of has an everlasting, kind of influence on with a very, very broad spectrum. In the recent time, with this advent of this and excitement with this twisted bilayer graphene, a lot of interest is also given on topologically non-trivial flat band that can generate because of the destructive interference of the wave functions in the lattice. And if one can have, and being a flat, it's actually a site of many different kinds of instability. And with the fractional occupancy of this flat band, there's also possibility of fractional quantum Hall effect. So therefore, it has called for a lot of. Well, I don't need to really talk about topology in this audience because it has been introduced, discussed at great length, but just for the sake of completeness, we start with the geometrical topology. The geometrical topology of the two objects is same. It can be deformed without singularity, and value of these orientable surfaces, genus is equal to number of holes. So if the number of holes is the same in two objects, they are assumed to be topologically invariant. Almost parallelism goes in the band structure topology, where two band structures are same if they can be adiabatically perturbed without gap closure. And topological invariant here is what cannot change unless the energy gap between the band closes and reopens. And underlying all of this idea is the Pancharathna-Berry phase, as has been also stressed quite a number of times in this conference and mentioned. So if you start from a block function, which is defined in the following manner, you can define a Berry connection, which is nothing but the k-space analog of magnetic vector potential. And once you define a Berry connection, you can define a Berry curvature by taking the curl of this A, which is the k-space analog of the magnetic flux density. And from there, one can basically define the first Chern number by integrating this Berry curvature over the 2D Brillouin zone and summing over all the occupied band. That defines the Chern number, which classifies basically the block bands with the non-trivial topology having a broken time reversal symmetry, which will give rise to the gapless chiral edge states of potential use in dissipation-less electronic circuits. In case of a T-invariant system, one can similarly define a spin Chern number or the Z2 invariant, and for each pair of the spin orbit coupled bands in the 2D will have a Z2 invariant, which essentially is the integral instead of the full 2D Brillouin zone half of this Brillouin zone. A lot of excitement, as I said, is also given to the topological flat bands, which will be in analog of the Landau levels in the electronic system. And this is kind of a comparison between the two. So you will have this lattice model with the complex hopping parameter, which will actually generate this kind of this Landau-like, mimicking the Landau-like levels, and this almost flat topological band with any Chern number being possible, time reversal symmetry being spontaneously broken by the magnetism compound. So therefore, there is no need to apply a very strong magnetic field as it would have been in an experiment with the Landau level. And as I already mentioned, the partial filling may give rise to the fractional quantum Hall state. Interestingly, the high temperature scale may be achievable as opposed to the case with the Landau physics. Well, but there has been a lot of interest given all this background. What is the search? What is the suitable material candidate? And there's a lot of discussion on this. And I will focus in my talk primarily on 3 different materials. One is the bilayer double perovskite, and I will try to kind of argue they can be a possible candidate for a room temperature quantum anomalous Hall. Then the second one is on binary intermetallics in Kagome lattice, and our calculation shows that they can be a possible host for a Chern metal or even topological superconductor. And the third one, if time permits, I will briefly mention, that's the graphene under deformation, and there are some kind of a replicated structure, the replications, which can host topological flat bands. For the oxide material, the double perovskite, this work was done in collaboration with my former PhD student, Shantu Boito, who after spending time in Duisburg and Seoul National University, right now is in Rutgers, Odun Paramakanti from University of Toronto, and Umesh Wagmare from JNCSR. Now, there has been a lot of interest on oxide materials in the context of topology as well, especially given this highly discussed paper, which actually suggested if you grow the oxide materials along the 1-1-1 growth direction, then the topology is that of a buckled honeycomb lattice. And this buckled honeycomb lattice, together with spin-orbit coupling, can give rise to a 2D time reversal invariant topological insulator. So that brings back the attention to the oxide materials even in the context of topology. So the motivation given this interest in quantum anomalous Hall, for practical use, one would like to boost the temperature scale of the topological anomalous Hall, as I mentioned, and therefore use d electrons rather than conventionally used S and p electron based system. Engineer a large topological band gap, avoid possible dopant or add-atom induced inhomogeneities like the original suggestions or the experiment where one doped the topologically invariant topological insulators with the magnetic atoms, or putting magnetic atoms on graphene and putting heavy atoms with large spin orbit coupling on the magnetic substrate. All of them were either add-atom physics or the doping induced thing. So which may lead to inhomogeneities in the system. So therefore, it's better if we can have it in a stoichiometric material. So with this motivation, we looked back to the double perovskite oxide. So I think a little introduction is needed in this audience. What is a double perovskite? Most of us know what is a perovskite. There the formula is AbO3, where the B is a transition metal site, and this is the structure of a cubic, ideal cubic perovskite, where all the corners are occupied by the A atoms. The B transition metal sits in the middle in the octahedral environment of the oxygen atoms, which goes and sits in the faces of this cube. Now you take this perovskite structure and make it double. Therefore, the formula becomes A2B2O6, and since you have B2 instead of a single B, you can afford to put 2 different transition metal, namely B and B prime, therefore making the formula A2BB prime O6, and the B O6 octahedra and B prime O6 octahedra, they have a kind of a rock salt ordering, alternate ordering along the all three directions. This class of compound actually is quite promising because there is a diversity of application. The compound which were initially brought a lot of attention to this family was strontium 2 iron molybdenum oxide, discussed heavily in the context of spintronics. Then came this bismuth nickel manganese, and the multiferroicity, very high temperature multiferroicity was discovered. The magnetodielectric compounds, and also there were theoretical prediction, then they can be used as magneto-optic devices. Now, taking this compound, since instead of one site, now you have two different sites, B and B prime, you can afford to put a 3D transition metal at the B site and 4D or 5D transition metal at the B prime site, and this conventional knowledge that the correlation effect is strong and it kind of weakens as you are moving from 3D to 4D to 5D, but the spin-orbit coupling basically strengthens as you are moving from 3D to 4D to 5D. So therefore, the idea is the following, that since I have a physical separation between B and B prime, so one of them, where I put a 3D transition metal, can allow for a high energy scale for magnetism, while 4D or 5D can feature strong spin-orbit coupling. And as I will try to show, that this low energy physics is basically described by the octahedrally crystal field split T2G bands, which are basically the low spin state of this 4D or 5D that suppresses heavily the Young-Taylor distortion, which has a tendency of converting this topological insulator to like a trivial insulator dominated by Young-Taylor distortion, as was discussed in the paper by Pickett, where he actually took several different oxide interfaces, and he actually showed that most of them, in spite of trying very hard, they turned out to be like a trivial insulator, because these were all EG physics, dominated physics, that made this Young-Taylor distortion very strong. Well, the compound that we worked on, I mean, I will try to show this can be a general mechanism, is this particular double perovskite barium 2 iron rhenium O6. This compound is a half metallic ferromagnet with a transition temperature of very high, like close to room temperature, and which is shown here. You see it undergoes a structural phase transition from cubic to tetragonal associated with a magnetic phase transition, and both happens at very high temperature close to room temperature. If you calculate the DFT electronic structure of this bulk material, which is shown here, the plus and minus being up and down spin channel, and the zero of the energy is set at the Fermi level, you see that the iron D states, which are shown in black, they are completely filled, while in the upspin channel, the rhenium T2G states strongly hybridized with the iron T2G state that crosses the Fermi level, therefore making it like an half metal because it's conducting in one spin channel and insulating in the other. So that's the bulk electronic structure. Now, what makes it a ferromagnet? This is like a hybridization driven mechanism, which was first discussed in the context of strontium 2 iron molybdenum O6. So the idea is the following: you have a large core spin sitting at the iron site, which is highly spin split, and the negligibly spin split rhenium states, rhenium T2G states, that falls within the spin split states of the iron. Now you switch on the hybridization between the iron and rhenium, that basically pushes this rhenium T2G states in the towards upward direction and T2G down in the down direction, therefore basically setting up a renormalized spin splitting and otherwise non-magnetic rhenium side, which is oppositely oriented to that of the iron. And by that, since all of the iron spins has to be oppositely oriented to the rhenium spin, which is an induced spin, the iron spins in the iron sublattice, they become parallelly aligned, driving the ferromagnetism. And these being completely determined by the hybridization, this can actually support a very high transition temperature. In a model level, you can think it like an effective two-side double exchange type model where you have a large core spin which is sitting at the iron side, and then this core spin interacts with the itinerant spin in a way it strongly favors one of the particular spin orientation of the itinerant spin. And this itinerant spin basically is a delocalized spin over this iron rhenium sublattice. So you can write like a two-side double exchange like model to explain its magnetism. Fair enough. Now we are back to the two-layer or bilayer of this particular compound, and we had kind of a quantum well-like structure where we put this bilayer sandwiched between the barium titanate. We have chosen barium titanate because they are lattice matching with barium. Iron oxide is actually pretty good. And this is grown along the 1-1-1 direction. Therefore, this structure, if you view along the z direction, you will see this buckled honeycomb-like structure where you have two triangles. One of the triangle is given by the iron sublattice and another triangle which is given by the rhenium sublattice. If you compute its density of state, it's pretty similar to that of the bulk, except that there is a significant narrowing of the bandwidth compared to the bulk density of state, and also there is Vanov-like features at the band edges which basically signals a dimensionality confinement by making such a kind of a quantum well structure, and that is seen also the plot of the conduction electron density which is strongly localized only at the iron and rhenium sublattice of this double perovskite. So by these we basically generated a highly confined half metallic 2D electron gas. Now what about the topological properties of it? This is the band structure in one of the spin channel, the conducting spin channel, the other channel being completely insulating. You see three of the bands that crosses the Fermi level, and they are basically the rhenium T2G bands. And this is the band structure in absence of spin-orbit coupling, and this is the band structure in presence of spin-orbit coupling. The spin-orbit coupling do have a significant effect by changing the details of the band structure. And if you calculate the Chern number of these three of these bands, they are kind of non-trivial. So these bands definitely have a non-trivial character, but since these bands kind of span a common energy window, the whole system remains like a half metal. So one can say that by this quantum well structure, what you manage to engineer is a topological half metallic band structure. So how can you make it insulating? We can make it insulating if we somehow can make these bands moving far from each other, and that is possible if you can enhance the crystal field splitting between these bands. So in the next stage, what we basically considered is like an overlayer substrate geometry. That means we have a substrate of barium titanate on top of which we had two layers of this double perovskite, which consist of an rhenium layer and an iron layer, and in between barium O3 layer. So in this configuration, the iron is in highly reduced connectivity. Instead of having 6 oxygen, this will now have 3 oxygen, and therefore the side symmetry at the iron gets reduced from the octahedral symmetry to a C3 symmetry, and that imprints very strongly on the electronic structure of rhenium. It still has 3 bands crossing Fermi level, but as you can see that because of this large trigonal distortion at the rhenium site, which comes from the reduced connectivity of the iron, it splits into Eg pi, doubly degenerate Eg pi, and singly degenerate A1G. That is the first important effect that happens in going to such a kind of a substrate-like geometry. And the second important thing that happens that there is a charge redistribution. in the bulk or quantum well structure, the iron was nominally in 3+ and rhenium was in 5+, so D5, D2 kind of combination, while in this overlayer it became iron D2, iron D6 and rhenium D1 configuration. So therefore, these 3 bands, instead of being occupied by 2 electrons, now becomes occupied by a single electron. And this is basically the electronic structure in absence of an spin-orbit coupling. This is still a half metal, but it is a half semi-metal because in the conducting spin channel, it basically is touching, the bands are touching only at the gamma point and having a quadratic band touching at the gamma, it being filled by only a single electron, which is in the D1 state, and that's your degenerate Eg pi level. Now you switch on the spin-orbit coupling that basically splits and opens the gap at the quadratic band touching. And if you calculate the Berry curvature, it has a very highly picked value close to the gamma point. If you integrate this Berry curvature over the entire 2D Brillouin zone and sum over all the occupied bands, that means summing over all of them, what you get, it has a kind of a highly quantized structure and its value at the 0 at the Fermi level being value of 1. So we managed to get the Chern number 1 topological anomalous insulator. And you can write a simple tide winding model and understand what is going on. You can start with a 3-band-like model of rhenium T2G. And if you put that in this buckled honeycomb lattice, what you get is a Dirac band touching at the Brillouin zone corners, which is the hexagonal Brillouin zone, which is shown here, and a quadratic band touching at the gamma. So you have like a Dirac-like band touching here and a quadratic band touching there. And what you have is a very interesting thing, another effect. Since the irons are sitting here and the rheniums are sitting there, there are this kind of the 2 triangle, the iron basically breaks the in-plane inversion symmetry of these rhenium atoms. And that gives rise to an in-plane electric field by this symmetry breaking, and which couples with the electric dipole that is formed by these two pairs of this non-Kramer's doublet of this Eg pi. And that gives rise to like a orbital Rashba type effect, which opens up a gap at this K point at the corners of this Brillouin zone. Now, if you include the spin-orbit coupling, that basically, and with the right filling, that makes it an insulator opening a gap also at the gamma point. And what about the high temperature? I started with the motivation that this will be a high temperature. So the strong spin-orbit coupling and the trigonal distortion that conspire to pin the rhenium moments out of the plane and making it a completely Ising-like. So therefore, if you do a Monte Carlo study of a mixed Heisenberg, because the iron spin still remains like a Heisenberg, while the rhenium spin behaves like Ising, you compute the TC because of this nice thing that your large trigonal distortion and the strong spin-orbit coupling makes it behaving almost Ising-like, but you get that the TC is even slightly higher than the bulk. So that means we have generated this kind of an anomalous quantum Hall state, which is operating at a very high temperature. So to conclude on this part, there are 3 essential ingredients. First of all, these bilayers of this half metallic double perovskite combination of 3D with 4D or 5D grown along 111 direction shows a strong trigonal distortion favoring a non-Kramer's doublet, which are basically Eg pi, and the bands in the conducting spin channel that features the Dirac band-like touching at plus minus K point and the quadratic band touching at gamma, and breaking this inversion symmetry of this iron that gaps out the gamma point, which is like orbital Rashba effect. And for an appropriate filling, which in this case is the D1 filling, it leads to a half semi-metal, which is what you observed in the GGA band structure. Now you introduce the strong spin-orbit effect of the 4D or 5D in this case, that gaps out the quantum, the quadratic band touching and making it an insulator, and this strong spin orbit and trigonal, they conspire to make the ferromagnetic Tc very high. And this should be a general mechanism, although I talked about a specific double perovskite. It should be a general mechanism, like you can consider iron molybdenum double perovskite, chromium tungsten double perovskite. All of them, by making such a kind of bilayer, it should be possible to drive a quantum anomalous Hall with a rather high temperature. Whatever remaining time, which is like 4 minutes or something, let's try to touch upon this Kagome Intermetallics, and this is the work done with Shantu and the team of Subhro with Abhash. I see Subhro in the audience, so any difficult question should be pointed to Subhro. And so if you have an isolated Kagome lattice, so that will be its band structure, which will host this flat band and this Dirac-like feature. And what are the corresponding material candidate? A lot of attention has been focused on this binary intermetallic Kagome series, where the T is the transition metal with this following choices, and at the X you can put either tin or germanium, and the M and N can actually have many different kinds of ratio. And these compounds actually show interesting features that is coming from the 2D Kagome layer, which is basically constituted by such transition metal side and the spacer atoms, and that is basically shown or manifested in terms of having Dirac-like feature, large anomalous Hall at room temperature, magnetic Weil points, and etc. Now, what about the flat band? And there have been this scanning tunneling spectroscopy, and that has been done on both these compounds, which are actually ferromagnet, and there are signature of this diverging density of state, but still the direct evidence of such flat band remains elusive, because in addition to such a kind of this 2D bands, there are also interfering 3D bands which are coming from basically the spacer atom, the tin or the sulfur. There have been in recent time also this iron tin compound where there is a photoemission, and they basically kind of points towards this flat band, but this flat band is several hundreds of MeV away the Fermi level. This is not really at the Fermi level. So can situation be made better? And what we suggested is, can one create 2D compounds out of these layered compounds? So the structure is the following. You have a bilayer Kagome and of this iron, in this specific case it's iron, and that is sandwiched between some thin layers and that are stacked on top of each other. From there, what we basically kind of created is a bilayer structure, which is a single bilayer of this Kagome layer, and which are sandwiched by these tin layers. And the Kagome layer, if you look at the interesting feature, is it consists of two different triangles, one a large triangle and a small triangle, and let's call the ratio of this large to small some parameter r. And what we found that, of course, you can calculate the cleavage energy, what will be necessary to make such a kind of 2D things, and we from the calculated value, which is like 1 to 2 joule per meter square, we think the creation of such a kind of 2D materials is possible experimentally. And by going to the 2D, a lot of changes happen in its electronic structure. Primarily, there is a huge dimensional influence, so there is a dimensionality reduction. So you have Vanov-like features if you look at in this bilayer density of state. The magnetism remains though pretty much like the bulk. It is a ferromagnetic object with ferromagnetic exchanges within the Kagome layer and out of the Kagome layer, which survives down to the bilayer. And if you look at the electronic structure, this is the electronic structure of the bulk material, and this is the electronic structure of the bilayer. Compared to the bulk in the bilayer, in the bulk there were a lot of states which were here, the fatness were proportional to the iron D character. So there are a lot of thin bands which are actually shows up in the electronic structure of the bulk, which kind of gets far more cleaned up if you go to the bilayer limit. And in the bilayer limit, this flat band shows up at the Fermi level, which are within the plus minus 10 MeV of the Fermi level. And if one computes the Chern number of these flattish bands close to the Fermi level, it shows the non-trivial Chern number. So therefore, there is a very good possibility it will be like a Chern metal. And the anomalous response of such a Chern metal calculated is also non-zero. So definitely, and this non-zero value can be obtained for a large range of R parameter, which is basically the ratio between the big triangle and the small triangle. So therefore, this kind of a Chern metallic behavior will be a robust feature in these bilayers of this Kagome compound of iron, or maybe it's even allied compounds. And there is also, which is a very much work in progress, that there can be actually a possibility of unconventional superconductivity. Since it's a low dimensional material, there can be possibility of magnetic fluctuation. So if you have a magnetic fluctuation driven pairing, which was computed by Avash, that shows a very interesting behavior. As you change the R parameter, there is a transition from a trivial superconducting phase to a topological superconducting phase, this phase hosting even number of Marana modes in its vortex core to an odd number of Marana modes in its vortex core. So therefore, to conclude on this part, my time is up. So this dimensional confinement to the bilayer of this particular layered intermetallics results in quasi-2D or 2D electronic structure. The survival of electron ferromagnetic correlation down to the bilayer limit, and importantly, there is realization of low energy bands with a suppressed bandwidth, which is almost flat band within plus minus 10 MeV of the Fermi level, and finite anomalous Hall response over a wide range of this asymmetry parameter, asymmetry between these triangles, which is a robust feature of a possible Chern metal. And this magnetic fluctuation can lead to an exotic superconductivity or even the fractional Chern insulating phase, which we are yet to calculate. So this is very much the work under progress. The last one, just one comment. So this is the graphene under deformation. So these layered solids like graphene or graphite, they basically deform by forming ripple-like structures or riplocations. So the riplocations are like pleated structure, and that is, there is a signature in the nonlinearity of the elastic property. I will not get into that, but this is the kind of a pleated structure, and if you can manage to generate such a pleated structure, its corresponding electronic structure shows the existence of such a flat band together with magnetism, and the calculated Chern number shows highly non-trivial value of such a flat band. So the graphene under deformation can be also a possible host for hosting such a kind of a flat band topology. So with that, I would like to thank you for your attention, and I'll be happy to any questions.
Thank you. Questions?
Yeah, sure. Yeah. You want this substrate geometry band structure?
The last slide of that.
This one?
Where you showed that spin-orbit coupling band structure, the 3-band model.
Yes. So you can have this one, I think you are referring to.
Yeah. So this is also ferromagnet. So in the ferromagnetic state, you should see also the spin splitting.
These are the 3 bands which are in one of the spin channel, because you have a very large spin splitting because it's a half metal. So the other spin channel is completely insulating to start with. without spin orbit, without anything. There is a very large spin splitting because of the spin splitting of the iron. Yeah. So this is basically therefore the 3 bands in only one of the spin channels.
So I had a question about the quadratic band touching.
Yes.
So is it sort of guaranteed by the symmetries of the
C3
lattice?
symmetry. Yeah. It
So
is, yeah.
any other sort of symmetry allowed terms won't split this into 4 Dirac cones or anything
No,
like?
I don't think so, because
Okay.
this buckled honeycomb structure of the lattice was very important.
Any more questions? If not, let's thank Tanusri.